That's great.
So our next speaker is Heather Macbeth from Fordham University, and it's also the opportunity for me to fill one gap of my opening talk. I forgot to mention that we also have 3 new maintainers for MathLib in 2020, including Heather, and the other two are Anne Bannon and Brian Chen. So I think Heather is our most recent maintainer, and she will talk about an example of manifold, and Kevin already guessed what was the manifold.
Thank you very much, Patrick. And yeah, I'm the newest maintainer, and I'm one of the people that has been part of the explosive growth in the last year. It's been really fun to join this community. What happened to my screen? Good. So I'll be making a manifold, and specifically the sphere. So this is a modestly sized project by MATLAB standards. The construction of the manifold amounts to, I suppose, about 1,200 lines of code, of which 300 is the manifold itself, and 900 is preliminaries of various kinds, mostly to the library on inner products, but some to other parts of the analysis libraries all over the place. And it's now all been PR'd, although it hasn't all been merged. And the, I guess, very first point I want to make is that this is a challenging intermediate exercise, but I mean, the reason that it's a challenging intermediate exercise rather than impossible is that we have this enormous manifolds library written by other people, and specifically by Sebastian Guazel. So this is a toy. This is a fun project designed to explore the manifolds library, but the real work has been done by someone else. I also want to mention that this is not new to formalization. So this was previously formalized in Isabelle, in their manifolds library, which came out a couple of years ago in January 2019 in CPP. So the Isabelle manifolds library, written by Fabian Imler and Boha Jean. Fun fact, Boha and I went to graduate school together when he was a low-dimensional topologist before he switched focus. So their project came out a couple of years ago, and as one of the things they did to test the scope of their library, they also formalized the sphere. So this is new to Lean, but it's not new to formalization. I want to also just briefly sketch what their work looks like. So this is the sort of final part of their code on the formalization of the sphere. You can see at this very last step, we have a manifold appearing. It's given by charts underscore sphere. I guess infinity is the degree of smoothness. And there's a check that certain lemmas are satisfied. And this is all very similar to what I do, with a few exceptions that I'll be mentioning as we go along. So I want to use this talk mainly as an exercise to see, how the manifolds library works. And my hope is that after I show you how to make one manifold, you all will be inspired to make your own manifolds. So think of this as a how-to guide. The first step is the library on local homeomorphisms. So let me maybe draw a picture. Let's say we've got two types. We've got alpha and beta, and we want to make a local homeomorphism, or to start with a local equiv between them. So what is that? Well, it's going to be a map, but only a partially defined map. And of course, you can't really do that. But what you can do is you can give full maps between the two of them, for which we only care about the behavior on certain sets. So we have these two types, alpha and beta, and we have an identified set called the source in alpha, and an identified set called the target in beta. And we have two functions, the so-called toFun from the source to the target, and the inFun from the target to the source. And let me repeat that these are actually functions defined on all of alpha and all of beta respectively, but for which we only care about the behavior on the source and the target. And we have these two hypotheses that they are left and right inverse to each other, as well as the pair of hypotheses that they really, in the region that we're interested to do, send each other to each other. And then a local homeomorphism is a local equivalence that is far more continuous and has open source and target. So these are pieces written by Sebastian, as all the RAIN infrastructure is, I guess, a year or two ago. Now, the local homeomorphisms are going to be the main component of making a manifold, so we need to figure out what the local homeomorphisms will be for the sphere. And for that, let me draw a picture. So I'm going to use stereographic projection of the sphere. So let me draw a sphere. If I have a fixed vector v, in my sphere, then I'm going to project onto the orthogonal complement of v. So here it is. And using mu notation, which I introduced in MATLAB last week, I'm going to write this as R scalar product with v orthogonal complement to represent the orthogonal complement of the span of the single vector v. And so this will be our target, this space here, and the source will be all of the sphere with the exception of the point v itself. And the map is going to take a point x, let's say, and send it off by drawing a line through v and x until I get to where it hits this blue line, and that's where the x is sent to. And I can do this over and over again and figure out where different points go. If I take a different point, like this one here, then it's going to be sent to here, and so on and so forth. And now a little bit of geometry lets us work out what the formula is for both the to fun and the in fun, so the forward and backward directions of this projection. I can say, maybe this is the source. So the to fun, I can work out by using similar triangles. So let me draw in, I can make a little triangle like this. And then I can draw a similar triangle, also a right triangle, that goes all the way to the orthogonal complement. It's going to look more like this. And that gives me a scale factor that I can use to work out where x is sent. So it's sent to the scale factor 2 over the inner product, 2 over 1 minus the inner product of v with x, dot product with the projection onto our orthogonal complement of x. This, incidentally, I'm going to use in the talk to mean the orthogonal projection. And I didn't make a notation for this in Lean, but maybe I should. So that's our formula for the forward function. And then we also have a formula for the inverse function. If I have a point w, which now is in the orthogonal complement, I'm going to send it to something which I can cook up by experiment and whose main feature is that it turns out to be a unit vector, namely 4w plus norm squared minus 4 dot phi all over norm squared plus 4. And then when you're making a manifold, the main thing is to check that the forward function and the inverse function, I mean, to be a local homeomorphism, these should be inverse to each other. So you have this rather terrible calculation where you check that these are indeed inverse to each other, both left and right inverse. To each other on the appropriate domains. So let me just show how one of these, the harder one, the left inverse calculation goes. Incidentally, I was reassured as I did this to notice that in Isabel, it's nearly as bad as in Lean. So it's not like our tools are that much lacking. So for x in the sphere, I'm going to split as scalar dot v plus w with w in the orthogonal complement. And then I need to check that 4 times 2w over 1 minus a plus 2w over 1 minus a norm squared minus 4 dot v all over 2w over 1 minus a norm squared plus 4. Oh my goodness, I want to expand this out. Maybe I'll clear the denominators. This is going to be 4 times 1 minus a dot 2w plus 4 norm squared w minus 4 1 minus a all squared dot v over 4 norm squared w plus 4 1 minus a squared. And as you can see, I deliberately didn't leave myself enough room to do this calculation in full. But I do some work and eventually I get back to a dot v plus w. And at some point in this calculation, you need to use the fact that we're in the sphere, which is the algebraic identity that a squared plus the norm of v squared, norm of w squared is 1. So this is the work that goes into making the local homeomorphism. And let me now indicate briefly what that looks like in Lean. So I have, after a period of preliminary work, I've defined this stereo 2 fun and this stereo in fun that we discussed. I write down their source and their target, which respectively are the complement of one point and the whole space. And I have all the different checks to show that it's a local homeomorphism. And so this is my completed local homeomorphism. And I just wanted to show what the worst of those looks like in Lean. This is the one I was just showing by hand, the fact that it's left inverse. So this is about half of it. It goes on and on. I found it most useful while doing this to do something that I'm not sure if it's sort of recommended style in Lean or not, but to somehow divide the problem into 2 parts, each of which could be automated. I actually haven't shown that part, unfortunately. It's sort of what happens at the bottom of the page, but you can somehow divide an algebraic calculation, or you can divide a calculation like this into one part, which is purely done by the simplifier. So all of the unfolding of definitions, and one part which is done purely by the algebraic things. So this is some combination of field simp and n-linearith and ring and so on. And I found this quite a useful idiom to make proofs clean, to divide it into these 2 pieces, which can be automated separately.
Heather, I have a question.
Yes.
So in the definition of a local homeomorphism, the source and the target are supposed to be open sets, but these are, I think, not open sets, right?
They are, right? One is, so they are open within the spaces themselves. So one is everything in the sphere except for the point V, and one is the universe within the orthogonal complement.
Okay, you're considering it as open sets in the subspace. Okay.
Yes, exactly.
Use topology. Could you say again what are the 2 steps that you find it useful to separate the thing in 2 steps? I didn't get the definition of the 2 steps. The abstract.
Yeah, sure. So, and unfortunately, I sort of did not include that part on my slide. But so the beginning here is here's the first one. So I separated out one step which consists of a couple of facts like this, which can be checked purely by some combination of, I guess, ideally a Grobner basis tactic. Although in this case, as I was telling Rob the other day, you can actually use n-linearith as a kind of cheating Grobner basis tactic. A fact like this can be checked purely by making the appropriate combination of this fact I was pointing out, that a squared plus the norm squared is 1. And after clearing the denominators, which is earlier fact. So you have this one sort of purely algebraic step, and then you have a second step where you reduce the problem, like where you sort of give it a whole bunch of simple lemmas for unfolding definitions and so on, and you tell it, okay, go off and apply the simplifier to reduce it to this algebraic calculation.
Okay, thanks.
The second step is to make a charted space, which is, I guess, mathematically more or less a topological manifold, but a topological manifold with, moreover, a choice of distinguished chart at each point. So again, I'm showing Sebastian's code here. This is the definition of charted space in MATLAB. And as you can see, it consists of, so an atlas, which is a set of local homeomorphisms, a choice of chart at each point, and the verification that indeed the point is in the chart and that the chart belongs to the atlas. And this is actually, I mean, it seems like it should be very straightforward, and it is, but the challenge here is deciding what to do. So let me point out something about these local homeomorphisms that I created. We have, namely, that for each V in the sphere, a local homeomorphism from the sphere to the orthogonal complement of that vector. And as we were discussing, the source is the complement of V in the sphere, and the target is the whole part of the orthogonal complement. And in order to make this a proper charted space, you can see that, so a charted space means that we select a model space, and that's H, seen here, that is the model. So our model space here is going to be Rn or some sort of vector space. And the problem so far is that in our, we have a local homeomorphism with a different target in each case. Like these orthogonal complements are going to vary depending on the vector that we choose as the base point of the orthogonal projection. So we need to identify the different orthogonal complements that appear. And there are two ways to do this. So the first way, which is the way that is done universally in the informal literature in every textbook you read, and is also the way that is done by Imler and John's method in their Isabel code, is that you fix a point V in the sphere, which we traditionally call the North Pole, and you use only the charts, that is the stereographic projection, for V and minus V. So this is the traditional method. You have two charts from the North Pole and the South Pole, which cover the whole sphere. And you can see how this is sort of psychologically beneficial for the learner, because it seems like you only have two charts, and that makes your life easier. But it's one of those cases where, in fact, I think it makes things harder for formalization. So the method that I used instead is to use instead as the standard chart at each point, the stereographic projection from the antipodes of that point. And now we need to, because now these orthogonal complements are all different, whereas the clever thing about these two is that they have the same orthogonal complement. So now that we have arbitrary orthogonal complements, we need to fix arbitrary isomorphisms from each of these orthogonal complements to some fixed Rn. And of course, this can be done because they're all the same dimension. At the moment, I've got it done for just finite dimensional spaces, but even in general, it should be possible, because if you have like a Hilbert space and you want to look at the complement of all of the different vectors in that Hilbert space, I mean, you can smoothly move one onto the other, and so they are still all isomorphic by some kind of Gram-Schmidt thing. But so this is actually a little bit more cumbersome to implement, but at the start, but easier when things go along. So you can see what I do. I make my variation on stereographic projection by combining the previous stereographic projection that I was telling you about with this brand new, as of this weekend, written by Adam Topaz, continuous linear equiv dot of Finden equal, which just says that if you have vector spaces of the same finite dimension, then they're isomorphic. And so this put together give us the actual charts that I use to make the manifold a charted space. And you can see now everything is very, very simple. You have this set of these modified stereographic projections as our atlas. We put the chart at each point as the stereographic projection from the antipodes at that point. And there it is. I mean, nothing could be simpler. Okay, and then, so now we have basically a topological manifold. We've shown that the sphere is a topological manifold, and the final thing is to check that it's a smooth manifold. And this means to check that the transition functions, so that is the result of first applying one and then applying another one in the opposite direction, are smooth. And I mean, of course, you know, that's the informal way of stating it. We have in Lane, again written by Sebastian, the formal definition of a smooth manifold with corners, which involves a bunch of things I'm not going to explain, you know, a has groupoid, and the times cont diff groupoid, and the model with corners, and so on and so forth. But for our purposes, the main thing that we need is that as soon as you have this definition, the very first lemma is the fact that in order to verify that you are a smooth manifold with corners, it suffices to check that if you take any transition, if you take any chart and compose it with the inverse of some other chart, then the result is times cont diff, which is lean speak for smooth. So you have the fancy definition, but you really do just need to check smoothness of a whole bunch of functions. And this was really the easiest part of the project. The library on smoothness of functions is very well developed. So you just apply lemma after lemma following your nose, and you get that all of the functions involved are smooth, and then you're done. So let me conclude by just mentioning a couple of things about the preliminaries, which I guess are not things you need to know to make your own manifold, but which are probably analogous to things you might have to do in a different context if you're going to make a different manifold. So the hard part of this library, as I was saying, was not actually the library on manifolds or smoothness, which is all extremely mature and well developed, but some work on inner product spaces. So I refactored the orthogonal projection library. I improved it in various ways. I made the previous linear map a continuous linear map. I changed the standard hypothesis on completeness from the old version to something that could be checked by type class inference. And I sort of bundled it a little bit more so that the codomain became the space you're projecting onto rather than the whole space. I introduced these new notations that I've been using in the talk. And I filled, I'd say, about 500 lines of essentially trivial gaps all through the library, everything from the orthogonal complement of the orthogonal complement as itself, to the dimension of the span of a non-zero vector, to a variant on the Cauchy-Schwarz equality case, to proving that the orthogonal complement is a closed subspace, and so on and so forth. Nothing more than 10 lines itself, but lots and lots of these things. And so let me then just conclude by by suggesting some exercises if this has captured your imagination and you feel like working on the manifolds library yourself. So firstly, I think it would be nice to have some examples of smooth maps. And two obvious ones would be the covering map from the line to the circle and the hop fibration from S3 to S2. If you're going to make the hop fibration, you need to sort of do it in a slightly funny way because we don't currently have projective space, which would be the natural way of doing it. But you need to just take explicit formulas for the hop fibration, which turns out to effectively be a quadratic map on R4, which restricts to the hop fibration on S3. So I think both of those would be fun exercises. Something else would be to, as I'm saying, sort of define the group weight of functions which are conformal, that is angle preserving, and to check that the transition functions of the sphere belong to this group weight. There's one little wrinkle there, which is that in order to do this, you have to, back where I modified my transition functions with an arbitrary linear equivalence between the orthogonal complement in Rn, you'll need to upgrade that to an arbitrary isometry between the orthogonal complement and Rn. So you need some version of Gram-Schmidt orthogonalization to do that. But beyond that, I think it's not too hard. And it could be quite nice, I think, to have that the sphere is actually a conformal manifold, and it provides a first chance to test the general group weights part of the library using a group weight that is not the group weight of smooth functions. You could make a bunch of other manifolds using this method, although it becomes sort of increasingly unwieldy, this method of explicit charts. So I think it wouldn't be too hard to write down charts for projective space. And if we, once Uri's refactor of sort of analytic functions and the exponential goes through, you probably could write down the explicit charts from the Lie algebra little son to the Lie group capital SON. That could be a fun exercise, although rather challenging. And then more generally using the smooth inverse function theorem, which I did over the summer, building on work of Uri's, you could put smooth manifold structures on the level sets of subversions or, on the orbits of group actions. But as you start to do these things, you'll see that there's also a kind of theoretical gap in what I did here, which is that I proved that the sphere is a manifold, but I did not prove that it's a submanifold of Rn, and I did not even define what a submanifold is. So that's because this definition is not currently in MATLAB. I tried it briefly and found it rather tricky, but I might try again at some point. So ideally, you want to have this stronger statement, not just that the sphere that I've made is a manifold, but that it's a submanifold of Rn, and the same for all of these things that I wrote down. So you want to make that definition and then verify it in these cases. And then finally, a little advertisement for the flagship project on geometry and topology in Lean at the moment, which is Patrick Masso's project on sphere version. So Merry Christmas, Patrick, and Happy New Year.
Thank you very much, Heather. Thank you for giving me the sphere, and thank you for your talk. It was really nice. So do we have questions for Heather?
No, you needed the sphere before you could invert it, right? Heather.
Well, actually, no. I mean, Patrick had a way of doing it without, I think, checking that the sphere was a smooth manifold. But
yeah,
I think it makes the result nicer, but I think it was not strictly necessary.
I mean, you can extend things to R3 and or at least I mean, you can extend to the complement of the origin in R3 every maps that are relevant. But it's much nicer to have the sphere as a manifold.
So Heather, this is great because it actually proves that all this manifold stuff actually works. I mean, this is the first proof that we have. Sebastian gave us a definition.
I mean, Sebastian also proved that the unit interval is a manifold with boundary.
Oh, okay. But that's linear, right? Do you think you could do Grassmannians?
I mean, I mentioned the projective space, and I think you could do Grassmannians as well. I'm not sure you would necessarily like to, but I don't think that it would be fundamentally very difficult. I mean, like, I think there's no theoretical abstraction. You just, in the same way that I had to fill in the inner product space library, you would find yourself really filling in the library on quotients and group actions and so on. So I think you would find that the preliminaries to fill in are not in the manifolds library, but in sort of the linear algebra library.
Linear algebra. The reason I ask is
charts by hand, you probably have less complicated calculation than for the sphere, actually.
Maybe. I mean, I think that what made the sphere tractable in this case was trying to do it as little by hand as possible, like working in this abstract setting of the inner product space and the orthogonal complement and so on, rather than writing down coordinates. And you'd want to do the same thing for the Grassmannian.
And you didn't show the computation for the coordinate change map, and this was not too
it's not necessary.
Oh, okay, because you proved it smooth as a composition of smooth things.
Using a machine.
Right? Okay. Great. And maybe one comment is probably about the fact that you use lots of charts and not only 2 charts. And in Isabelle, they use 2 charts. I think in Isabelle, they don't have a choice because the situation is very asymmetric for them because of their simple type constraint. Even saying the unit sphere in R to the n+1 is tricky in Isabelle. So they have to break symmetry in Isabelle. So they couldn't use your atlas, I think. At least it would be very inconvenient.
Another exercise you could add to your list is to show that rotations are smooth maps. And is that something that's easier to do when you have is it easier or like harder? Actually, I don't know. But
actually, that's a great exercise, and I don't think it would be particularly difficult. I mean, what you would say is that you know, a rotation is the restriction to the sphere of a linear map, and a linear map is automatically smooth, and so I think that would be a good and not especially difficult exercise.